Alright, hi guys. Today we're going to be looking at first part of section 4.3 notes. There's some other questions that go with section 4.3 that we will focus on when we're not doing anything else so that we can focus on them. But the rest of section 4.3 is all about Sohcahtoa and showing you some of the basic identities that you need to memorize. So Sohcahtoa is something that you learned back in geometry course. So hopefully this sounds familiar to you. If it doesn't, it's really big on the ACT. I think you can always expect like 1 or 2 of the 60 math questions on the ACT to be Sohcahtoa questions. So it's good review for that, but it's also important for calculus. So the first note here, I've got it super highlighted for you. Just because section 4.2 was about memorizing the unit circle and using it a little bit. If you still haven't mastered that, you need to put some time and effort into that because it's going to just keep getting used, including in this section a bit. Okay, so the whole point of the acronym Sohcahtoa is that the first 3 letters remind us that sine is opposite over hypotenuse. The next 3 remind us that the cosine ratio, we can take adjacent over hypotenuse, and tangent is opposite over adjacent. So this is true when you have a right triangle. If it's not a right triangle, you can't use Sohcahtoa, but those ratios give us those equations. All right, and now we've already talked about the reciprocal functions, so we actually know those as well. If sine is the reciprocal of cosecant, then you can think of cosecant as hypotenuse over opposite. Secant's the reciprocal of sine, so you could think of it as hypotenuse over adjacent. And since tangent and cotangent are reciprocals, cotangent would be adjacent over opposite. So we really know the reciprocal ones already as well. So what Sohcahtoa can do for you is if it's a right triangle, sometimes we use it to find side lengths, and then sometimes we use it to find angle measures. Alright, so let's go ahead and do a couple of examples of finding side lengths, and then we'll do a couple examples of finding angle measures. Alright, so there's my right triangle, and let's say I wanted to find this side length. Well, I could tell you that this is 3 and this is 5, and you could use Pythagorean theorem, and Pythagorean theorem is a great tool. We're still going to use it sometimes. But let's say I don't tell you this length, and instead I said, I don't know, maybe this angle here is 20 degrees. So I can't use Pythagorean theorem, I don't have the right information from that, but I can do Sohcahtoa. From this 20 degree angle, if I'm trying to find the opposite side, opposites directly across, and I know adjacent side, adjacent is next to but not the hypotenuse, then I can use tangent, because tangent of that angle will always be opposite over hypotenuse. Okay, so there's my equation. Now I still need to solve it for x if I want to know what x is, but that's super easy. Undo divide by 3 by multiplying by 3, and it looks like that length with those made up numbers would be 3 times the tangent of 20. Typing that in my calculator, making sure my calculator's in degree mode, and that's about 1.092. So if this length is 3, this one being a little over 1 seems to be kind of in the same ballpark. Alright, so very similar. Let's say I have a right triangle. I'll even keep the angle the same. But what if I wanted to find this length and that length was 3? So these two questions almost look identical, so a lot of the same work goes behind them. It would still be tangent because you know opposite and you want to find adjacent, and tangent's the only one that pairs up opposite and adjacent. Sine would pair up different stuff, cosine pairs up different stuff. But this time when I say tangent of that angle, it's always opposite on top and adjacent on bottom. So making the equations not any harder, but now to solve this, it's just going to take a little bit different algebra. So what I usually do is I just swap these two around. I know x is going to equal 3 divided by the tangent of 20. Until you understand why, though, you really shouldn't take that shortcut. So you could multiply both sides by x so that you didn't have fractions. And then tangent of 20 is just a number. So undo timesing by tangent of 20 by dividing by tangent of 20. And you get x is 3 divided by tangent of 20. My calculator tells me that is about 8.242. Okay, so depending on if the side you're trying to find is in the numerator, it would solve like this, or if it's in the denominator, it solves like this. But to make those equations, you've got to use your Sohcahtoa acronym. If you're trying to pair up opposite and hypotenuse, you would make a sine equation. If you're trying to pair up adjacent and hypotenuse, if you're trying to find either one of those when you know the other one, you would do cosine, and then of course tangent, as I did on those two. So if you remember doing this in geometry, that's probably what you remember. I'm sure you also did angles, although it seems to be the one that people sometimes forget. So it has to be a right triangle. Let's say this angle is 10 degrees. Well, if you have this situation, it's kind of like up here. If I knew 2 of 3 sides, I could use Pythagorean theorem to find the third side. So I didn't need Sohcahtoa. And then same with this angle. If I know 2 angles, I know all 3 angles of a triangle add up to 180, so I know that angle has to be 80 degrees, given those measurements. But what if I'm not told this angle, and instead I'm told, here's theta, that's the angle I'm trying to find. What if I'm told this is 4 and this is 5? So from this angle, I'm trying to use adjacent because I know its length, and I'm trying to use hypotenuse because I know its length. So that can't be sine. Sine doesn't use adjacent and hypotenuse. It would be cosine, not tangent. And so you could start off saying the same thing. The cosine of that angle is the adjacent length over the hypotenuse length. But what you're solving for here is how big is that angle? So to switch this from cosine theta equals to just theta equals, you can do inverse cosine. So the inverse, I used to teach quite a bit of geometry back in the day. And in a geometry course, I could just simplify it by saying, if you're finding a side length, use the regular trig functions. Use regular sine, regular cosine, regular tangent. But if you're trying to find an angle, you need to do inverse sine, inverse cosine, inverse tangent. And that's built into the calculator also.
Attention, students.
All right, sorry about that. So that's built in your calculator. Just instead of hitting the cosine button, I hit the second cosine button to get inverse cosine. I went ahead and typed that in. My calculator's in degree mode, so there's my answer. All right, let's throw out another one. What if I knew this length was 10 and this was 24? Has to be a right triangle. And you were interested in finding that angle. So this time you know opposite, because it's directly across. You know hypotenuse. Hypotenuse is opposite the right angle. And so from Sohcahtoa, this time I would want a sine equation. So sine of that angle is opposite over hypotenuse. And to switch it from sine theta equals to just theta equals, I switch it from sine to inverse sine, but it stays the same ratio. It still stays opposite over hypotenuse. Throw that in your calculator. If you want degrees, make sure you're in degree mode. And nothing else to it. Don't overcomplicate that. Alright, so maybe you have forgotten some of that, but I'm sure you've seen all of that in a geometry classroom, and then very important for ACT. So it'll be important for us in this class for a little bit, but more importantly for the ACT for you. Alright, let's say we were given 2 lengths of a right triangle. That can be enough information to find all 6 trig functions. So you'll have some questions that ask you about this, and so let's just throw out an example. It's got to be a right triangle. Okay, that's a pretty sad right triangle. Alright. And then we're going to talk about one of these acute angles. So you don't have to use theta, but theta is pretty common. And if I knew this length was 7 and this length was 10. Alright, well, if I'm asked for all 6 trig functions, they're saying what is the sine, cosine, and tangent, and the reciprocals. So I like to line these up, since these are reciprocals and those are reciprocals and these are reciprocals. Lining those up reinforces which one is which for me. So as it stands, I know opposite and hypotenuse, so I know sine, and of course I could flip that over to get its reciprocal. But to find the other ones, I'm going to need to know adjacent. Cosine is adjacent over hypotenuse, tangent is opposite over adjacent. They both need adjacent. So if I want to know this side, and I know 2 of 3 lengths of a right triangle, we can do Pythagorean theorem. Very useful tool for us even in pre-calculus. Alright, so what's that? 51, square root of 51. Okay. Now, sometimes you'll need to reduce that radical as well, but 51, I believe, is prime, so I don't need to split that up. So cosine, I could do adjacent over hypotenuse, and then I could flip that for secant. Tangent, I could do opposite over adjacent, and then I could flip that for cotangent. Okay, so there's all 6 trig functions. There's 2 of them I need to put a little more work into, though. So look at my 6 answers and see if you can determine which ones need more work. Okay, it's going to be this one and this one. Remember, we don't like to leave radicals or square roots in our denominator, but we can fix that. Multiply the top and the bottom by that square root, and you get 10 square root of 51 over 51. Do it over here. You get 7 square root of 51 over 51. So those 2 just take a little bit more work. But there's all 6 trig functions, and then that's how that would work out for you. Alright, the other part of this unit is there's some basic identities that you need to memorize so that you can use them. You have to recognize them before you can apply them. And there's a few of them that we've already seen and we've already worked with at least a little bit. So reciprocal functions are certainly ones that we have used some. So that's like knowing cosecant is the reciprocal of sine, and I could write it the other way as well. Sine is the reciprocal of cosecant. Secant of an angle is the reciprocal of cosine of that angle. Cotangent is the reciprocal of tangent. Okay, you've seen those before. I guess technically there's 6 of them though. I could switch these around and switch these around. Okay, quotient identity. You should know the tangent one now. Tangent is sine divided by cosine. And so technically cotangent is also 1. But since these are just reciprocals, you can just flip it over. Okay? When we did the unit circle unit, we first started talking about sines, cosines, tangents, and the others in terms of x, y, and r. So you may want to go back and watch those 4.2 notes again if you want to know where these come from. But let's see, sine was y over r, this was x over r, tangent was y over x. So I could flip this one for cosecant, flip that one for secant, and flip this one for cotangent. Okay, so remember like how sine is equal to y on the unit circle? That's because r was 1. Cosine is equal to x on the unit circle. That's because r was 1. So that's how I can keep a couple of those ready to go. I showed you, but you haven't had to use too much, the difference between even and odd functions. So you need to know which trig functions are even and which ones are odd. The 2 even ones would be cosine and its reciprocal, And what it means to be even is whether you plug in a positive angle or a negative angle, you get the same thing. And then the other 4 are going to be odd. So sine, its reciprocal, tangent, and its reciprocal. They're not equal to the same thing because that would make them even. But they're equal to the opposite of the same thing. So if you multiply one of them by a negative, now they're equal. So you need to be familiar with those even-odd identities so that you can apply them sometimes. Very, very important one is the Pythagorean identities, and it's really just an extension of the Pythagorean theorem that you're already aware of. So imagine if I took a point, x, y, and I made this my circle, kind of like we do with the unit circle, and I draw this down to get a right triangle. Well, this length would be x, this length would be y, and this length would be r, just the radius of the circle. So I guess I could say, well, it's a right triangle, so let's do a squared plus b squared equals c squared. But my a could be x, my b is a leg, so it could be y, and my hypotenuse I'm calling r. Alright, well now we're getting pretty close, because now if I take it one more step and I say, wait, let's make this the unit circle, 1 squared is 1, and if it's the unit circle, cosine equals x. So instead of saying x squared, I could say cosine squared. And when it's the unit circle, sine equals y. So instead of saying y squared, I could say sine squared. So cosine squared plus sine squared equals 1. I'm going to go ahead and flip those around. We usually say sine squared plus cosine squared equals 1. It's the same thing. It's just always written that way by most textbooks. So there's the first Pythagorean identity. It's really just a Pythagorean theorem, but instead of a, b's, and c's, I use x, y's, and r's. And then I changed it to a unit circle, so this became a 1, this became a sine, this became a cosine, and there's the first one. Now if you memorize this one, you can apply it to find the other 2. There's 3 Pythagorean identities. So what I say is memorize this one, and then go back and divide everything by sine squared. So sine squared divided by sine squared is 1. Cosine squared, well, cosine divided by sine would be cotangent. That's a reciprocal identity, or a quotient identity. It's one of those things. So you don't know how to use it there if you don't know that. So a cosine squared divided by a sine squared would just be a cotangent squared. And then 1 divided by sine squared, well, 1 divided by sine could be cosecant, so 1 divided by sine squared would be cosecant squared. So there's the second one. Divided the first one, that's easier to memorize, divided them all by sine squared, and I derived the second one. You can also find the third one by dividing everything by cosine squared. So divide this by cosine squared, this by cosine squared, and this by cosine squared. As long as you divide everything by the same thing, it is fine. And there's the third identity. And I'll be honest with you, I honestly do exactly what I'm about to tell you to do. I have this one memorized, and then each school year when I start using these more, I just divide them all by sine squared to figure out this one, and I write it on the top of my page when I need it, and then I divide them all by cosine squared to write out this one at the top of my page when I know I'm going to need it. Now after a few weeks I kind of like remember it where I can just do it from muscle memory, but early in the year I do the same thing that I'm advising to you. Alright, and then the last of the basic identities that you need to memorize to just kind of get your feet on the ground is some of the cofunction identities, and these will make more sense to you when we talk about what the graphs of these functions looks like. So cofunctions, they kind of come in like 3 groups, or I like to think of them in 3 groups. So sine and cosine are cofunctions. Secant and cosecant are cofunctions. and tangent and cotangent are cofunctions. Now what that means is you can find the sine of an angle by doing the cosine of 90 minus that angle. Or vice versa. You could find the cosine of the angle by doing the sine of 90 minus that angle. So what that means is, like let's say you wanted to know the cosine of 30. Well, the cosine of 30 is the same thing as the sine of 60. And since you now know the unit circle, that makes sense to you. You know that the cosine of 30 is equal to the sine of 60. But this is always true. The cosine of 1 degree is the same thing as the sine of 89 degrees. Maybe you know the sine of 89 degrees, but you don't know the cosine of 1 degree, so that's where that can be helpful. Where it's going to be helpful later with the graphing is these two graphs look very similar to each other. So these work out the same way. This is secant of 90 minus theta gives you cosecant, or secant you could get by doing cosecant of 90 minus theta because they're cofunctions. And exactly the same pattern here. If you wanted to know tangent, you could do cotangent of 90 degrees minus that angle, or if you wanted to know cotangent, you could do tangent of 90 minus that angle. So short term, it's not too useful. It'll take a few weeks before you can appreciate these, but again, notice the pattern, like the pattern of all of these. Really, you just need to memorize the pattern, and you need to know that these two go together, they're cofunctions. These two go together, they're cofunctions, and those two go together, those are cofunctions. And that'll be enough to help you memorize those. Okay, so again, some of it you've seen before. Hopefully you don't have to memorize. Some of them you'll have to look over. Some of them you need to practice deriving a little bit. And some of them you just need to be careful with how they're written. But it is something that you need to memorize so that we can use them, and we'll be using those in class shortly. When I first started this video, I talked about 4.3 is kind of split into two sections. Well, the second part of this, or two parts, the second part of this is heavily dependent on you having this memorized. I will also include on the website some flashcards that were made to help you practice studying these, so please take advantage of using those if you need to. That's all I've got for you on the 4.3 notes, so you should be good to start practicing. You might want to skim through the notes real quick and then move on to the assignment I'll leave for you.